Moving from building stateless chat interfaces to deploying autonomous, non-deterministic reasoning loops requires a complete reset of how engineers think about failure. Standard language models end transactions if an answer is bad, but agents rely on a continuous reasoning loop, assessing, selecting tools, and evaluating. Mid-task errors don't stop execution. They get written into memory, contaminating the context that downstream steps depend on. Traditional error handling fails here. A standard try-catch block is designed to catch a malformed payload or a network timeout. It cannot catch an agent generating perfectly valid JSON that relies on completely flawed logic. Developers break agents when they treat them like standard software, operating under the assumption that adding more nodes, adding more tools, and more code inherently increases capability. To understand why this fails, we are going to build a production-ready agent from first principles. We will identify the specific architectural anti-patterns that guarantee system collapse and replace them with the structural constraints that actually work. Production readiness for AI agents requires designing for the compounding nature of state, rather than optimizing for isolated outputs. When faced with automating a complex task, an engineer's initial instinct is usually to design a hierarchical multi-agent network to divide the labor. Multi-agent systems generate immense coordination overhead. Transferring data between models compounds token costs and latency unpredictably. It's also a debugging nightmare. A subordinate agent's hallucination cascades opaquely through downstream orchestrators, producing visible symptoms only at the top. To avoid that routing complexity, teams often swing to the opposite extreme, building a God agent, a single instance overloaded with dozens of tools and sprawling, conflicting system instructions. The mathematical consequence of the God agent is that optimizing system prompts for one specific edge case actively degrades the model's baseline performance across its primary responsibilities. Reliable architecture starts here: a single, highly scoped agent. You must fully validate that this narrow setup can solve the core problem before you ever introduce a second node to the environment. You only split this architecture into a multi-agent topology when you have measured exactly where the single-agent routing breaks down, and when the business value explicitly justifies the token cost of coordination. Sophistication is not a goal. Narrowing an agent's scope and specializing its function is the only reliable method to scale accuracy. Once the agent is scoped, we have to define its tool surface. The reflexive move is to grant the model tools for every conceivable scenario it might encounter. This introduces tool sprawl. Every new tool added to the context is a new variable the model must evaluate during every step of its reasoning loop. The internal attention mechanism maps user intent to specific actions. Clear options create a sharp selection spike. But when dozens of overlapping tools flood the bounding box, the probability distribution flattens, fracturing routing logic and causing unpredictable tool selection. Massive descriptions for overlapping tools artificially inflate prompt size, cannibalizing reasoning tokens. We fix this with strict modularity. Engineering tools as discrete zero-overlap modules restores a clean, definitive spike, allowing the model to distinguish its options. If you find yourself writing highly specific tools just to handle bizarre edge cases, it is a signal that the task scope itself needs to shrink, not that the tool list needs to grow. Tool selection accuracy is inversely proportional to the volume and overlap of the tools provided to the model. Designing memory for this agent requires discarding the standard chatbot paradigm. Simply passing the entire conversation history forward will instantly crash an autonomous, multi-step task. This diagram illustrates the phenomenon of context rot. The context window is a finite resource. As token counts climb over long executions, a model's ability to accurately recall information measurably degrades. Unedited tool outputs are the primary cause. Dumping massive database returns into memory generates cognitive noise. As these dense data blocks fill the context window, vital system instructions are compressed and pushed entirely out. The agent forgets its rules. To prevent this, you implement a 3-layer memory architecture: short-term session state for tasks, long-term vector stores for context, and structured audit logs for debugging. In practice, this means enforcing hard output size ceilings on your tools. Instead of dropping a full dataset into the context, the system must parse out only the exact values the agent needs to move forward. You combine this with automated pruning protocols that clear out stale intermediate tool results as the agent approaches token limits, preserving only the essential logical flow. Treating the context window as a finite, heavily curated resource is the only structural defense against mid-task hallucinations. Building the architecture is only half the problem. Next, we transition these scoped agents, modular tools, and layered memory systems into a live production environment. Production exposes a harsh reality. Because models are non-deterministic, your agent will eventually reason incorrectly, executing that wrong action with absolute statistical confidence. This makes the operational anti-pattern of granting an agent default, ungoverned write access to live databases or external user emails exceptionally dangerous. This schematic outlines the mandatory segregation of risk. Read operations are low risk, but write operations must be physically intercepted by strict validation logic before execution. For high-stakes or irreversible actions, you configure those guardrail nodes to enforce human-in-the-loop confirmation. The agent drafts the database update, but a human approves the commit. When an agent hits one of these guardrails and fails, you need to know why. Standard software stack traces are useless here because they cannot expose the opaque reasoning process that led to the bad decision. You must build distributed tracing into the system from the first line of code. This provides total visibility into the prompt chain, the exact tool parameters the agent hallucinated, and how context flowed between steps. Production readiness is not defined by the extent of an agent's autonomy, but by the strength of the governance and observability boundaries that constrain it. This final blueprint shows a durable architecture. We rely on a single specialized agent, discrete tools with zero overlap, heavily pruned layered memory, and governed write access. But there is a final hurdle. Testing this system exclusively against predictable, happy path examples in a controlled environment generates total false confidence. Standard QA checks fixed inputs and outputs. It completely misses the cascading, compounding edge cases that emerge when an agent manages state across 10 successive reasoning steps. You must subject the architecture to adversarial evaluation. This requires injecting intentionally corrupted data, feeding the agent edge case prompts, and purposely causing tools to fail to ensure the reasoning loop can recover. The success metrics for these stress tests must be tied directly to business outcomes, like correct database updates or resolved support tickets, rather than relying on abstract internal model benchmarks. When an autonomous agent project stalls, the underlying language model is almost never the actual bottleneck. True agentic capability comes from ruthlessly subtracting noise, managing state over time, and scaling complexity only when forced by hard data.